here click something. On the Zoom, can you hear me? Hello?
Hello, can the people in Zoom hear?
Yeah, we can hear you.
Okay.
Thank you very much.
Start now. Okay, so in this lecture, we are going to learn the first part of section 4.1, derived distributions. So first, let's recap a concept of the PDF of a continuous random variable. What's wrong?
Too bright.
So first, let's recap the concept of PDF for random variable. Continuous X negative function called the PDF of X. That X belongs to region B is equal to the integration over this PDF function fx. So this function here is called the PDF of a continuous random variable X. So this is what we have learned in the previous lectures. So for now, we are going to move on to discover deeper. So consider functions equal to gx. And we want to find out what's the PDF of y. And this is also called the derived distribution. So derived distribution is actually the PDF of y, and y is a function of x. So how can we obtain the PDF of y here? We need to follow a two-step approach. Step one. First calculate the CDF of y. Using this formula here, the CDF of y is equal to the probability such that gx is smaller or equal to y. So this is just a definition of the CDF of y, and this is equal to, and since we already know the PDF of x, so we can integrate over the PDF of x, and then we get this. So the cumulative distribution function of y is just equal to this formula, right? And given the CDF of y, we just need to differentiate it over y, and then we can get the PDF of y. Let's star, differentiate star to obtain the PDF. This is a two-step approach. So first, we derive the CDF of y using the PDF of x, and then we derive the PDF of y by differentiating the CDF. So if there is no question about this approach, then we can move on to the example. Let's give an example first. A very simple example. Let x be a continuous random variable that is uniform on 0 to 1. And we let y to be the square root of x. Okay, so since we know that x belongs to this region from 0 to 1, and y must belong to 0 to 1. So then we implement this two-step approach. So for step 1, the CDF of y, which is equal to the probability of square root x is smaller than y. And then we can take the square on both sides, so we can get the, x smaller than y squared. And since we know that the x is uniform on 0 to 1, so we can integrate this probability as follows. So for now, we already have the CDF of y, then we take the step 2, and then we get the differentiation. It's easy to calculate this differentiation, so which is equal to 2y. And this holds for all y in 0 and 1. So, and we also need to know that for y does not, like for y smaller than 0, the CDF of y only belongs to 0 and 1. So this probability is equal to 0. So the CDF of y is equal to 0 when y is smaller than 0. And similarly, for y greater than 1, since the y here is already greater than 1. So this probability is equal to 1. Then this gives PDF of y is equal to 0. So for y in 0 and 1, the PDF of y is equal to 2y. However, for y outside this interval, we have that the PDF of y is equal to 0. To understand this relationship, this is the 0 and 1. So the conversion is 0. So this is a slope equal to 2y. So you can't hear me clearly, right? Hear me clearly for now? That I'm cutting out from. Oh, okay.
Sometimes there's input issue.
Problem.
The problem is a short moment. Sean, is it better? It's better. Everyone is better.
Hello?
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 Okay.
Oh.
System. Hello, is this better?
Now? Sounds better now, right?
I think you just have to speak a bit louder.
Okay.
Yeah.
Okay, I see.
You just have to speak a bit louder. Okay. So let me do right here, okay? And then let me.
Okay. Okay, sure. Into the computer. Also, I need to stand like here.
Yeah, right. Yeah.
Okay, I see. Okay. Okay, so now we finish this example, and then if there is no question, then we move on to the next example, a more complicated one. Okay. So let's give a scenario. For example, John wants to drive from Boston to New York at a speed of random variable. So the speed is a random variable x, which is uniform. 30 and 60. And from Boston to New York, there is 180 miles distance. So we assume that the John is driving at a constant speed, but this speed is a random variable. We don't know whether the speed is 30 or 60 or 50. So, and we want to calculate the travel time. So the travel time is equal to 180 over x. So this is a simple calculation. And then we want to find out what's the PDF of y here. So still, similarly, we just follow the two-step approach. So at step 1, we find out the CDF of y. This one is equal to the probability of 100 over x smaller than y. Since x and y are both positive, so we can move them. Then this probability is just equal to the integration x greater than 180 over y of the PDF of y of x. Yeah. So let's write out the PDF of x first. X is uniform on 30 to 60. Otherwise. Is 60. To do this integration here, we need to discuss different cases since we don't know the value of 180 over y. Integration. Discuss 3 cases of different values of y. First, if 180 over y is greater than 60, which means y is smaller than 3. So that's greater than 180 over y, we have y is equal to 0. So that we can obtain this integration here is also 0 because fx is 0. So the CDF of y is 0 for y smaller than 3. Second case is when 180 over y is in between 30 and 60. So which means y is in between 3 and 6. So in this region, in this interval, for any x greater than in this region, so from 180 over y to 60. Which is equal to cases when y is smaller than 30, so y is greater than 6. And again, for any equation here, first, we integrate from this to 30 fx 60. And this is equal to 1 over 30. So 1. For the 3 cases, by discussing 3 cases of the values of y, so we obtain the final CDF of y. So in question of this, so in similar questions, we need to remember that we always need to remember that different values of y will is quite different for the result. Then based on this CDF, we just do the differentiation and we can get the PDF of y. And it's over 1 square if seeing that if we follow this 2-step approach, we can easily obtain the PDF of y at the end if we just follow every step clearly, correctly. Figure of the CDF to better understand. 3 to 6, 3 to 6. For y smaller than 3 is 0. And then it will increases to 1. Yeah, this is the CDF. So at the end, the CDF will increase to 1. And CDF is always smaller than 1 because it's a probability. From this figure of CDF, we can see that first for y smaller than 3, the differentiation is equal to 0. And for y greater than so equal to 0 for y greater than 6, and in between it's like something like this. Strange, but it is what it is. Step 2 be 1 instead of 0. Do you mean the PDF of y here? So the CDF of y for y greater than 6 is equal to 1. So after we differentiate this 1, yeah, so the differentiation is equal to 0. Yeah, right. Oh, okay. Oh, I see. Yeah, so we can see that actually the PDF of y is the derivative of the CDF here. So this is flat, so the derivative is all 0. And this is this interval corresponds to this one. Yeah. Let's move on to the next example. This time we assume that y is equal to the square of x. Just assume that the PDF of x is known. But we don't know what it is, but we only know that this is given. So we want to find out the PDF of y here. Still follow the two-step approach. So first, we need to know that y is equal to x squared. So y must be a greater than non-negative value. Yeah. CDF of y, which is equal to the probability of x squared smaller than y. And this can be written as, so by taking the square root on both sides, we obtain this inequality. This one is just equal to the gap between the fx square root y minus fx minus square root y. So for now, we can represent the CDF of y using the CDF of x here. Step 2, that is the differentiation of, doing the differentiation of the CDF. Just plugging this thing to here. How can we solve this differentiation? Because here we only have the square root of y, but here we are differentiating over y. So we can apply a technique here. Maybe you haven't learned it before, but you can just remember it. Instead of differentiating over y, we differentiate over square root y here. First can be written in this form. We just add this two term here, which can be canceled out, and it doesn't affect the result. The second part, we can do something similar. We call this technique the chain rule. That we so that this differentiation can be calculated because this part is just equal to the PDF of x where the of square root y. term. We have this. In the differentiation of this part, we are just regarding the square root of y as a whole term, as some random variable. So it's just like differentiating over x, fx, x. So we obtain the PDF of x here. An example when we know that the PDF of x is given, but we don't know the form of the fx. So we can use this technique to represent the PDF of y using the PDF of x. No question. Then let's move on. This example, we assume that y is an exponential function of x. Continuous random variable uniformly distributed within 0 and 1. Write the PDF the same question. We want to find out the PDF of y here. Step 1, we still calculate the CDF of y. And here, this is an exponential of x smaller than y. So by taking logarithm on both sides, probability of x smaller than log y. So this is equal to the fx, big fx of log y. So here we still need to discuss different cases of y. Y in between 1 to e, which means x is in between 0 and 1. So we can see that the CDF of y from 0 to log y over fx. And fx here is equal to 1. So we obtain log y here. Y smaller than 1, which means log y is smaller than 0. So CDF of y here is equal to minus infinity to log y, where the fx is already 0 in this interval. So we obtain 0 here. When y is greater than e, which means log y is greater than 1. It's just equal to 0 to 1. And this is equal to 1. So fy is equal to 1. Then we can differentiate the CDF to obtain the PDF. For PDF, we need to discuss different cases of y. Right. For y in this interval, the PDF of y is equal to this differentiation over y. One over y. Outside this interval, the CDF is already a constant number, so the differentiation is equal to 0. This is the similar steps, just but the function is different. When we do the calculation, we should always be careful about the interval of the values of y and x. The final example of this part. Variable. The PDF of x is given by this y be 1 over x. So find the PDF of y here. Step 1. Y. Y smaller than x. For any x in 0 to 1, we have that y1 over equal to 1 over s is equal to 1 to infinity. So here this Where's the inferred? Oh, sorry. Yeah, this is, sorry, I don't know. This symbol stands for all. So here we notice that x and y are both positive values, so we can switch them here. And then we do the integration. One minus 1/4 y to the power of 4. Smaller than 1. Someone is speaking? Smaller than 1, the CDF is just equal to 0. Step 2. We derive this 4/y to the power of 5. And for y smaller than 1, fy is equal to 0. So the previous examples are just some general cases such that y is a function of x. And if we specialize it to the linear case, where y is a linear function of x, y is equal to, for example, y is equal to ax plus b. And let's give an example here. For example, y is equal to 2x plus 5. Example, first we plot the figure of fx, that is the PDF of x. We say that this is the PDF of x. And then the PDF of 2x is as follows. The PDF of 2x. And then by adding 5, we just move the PDF to the right to 5. 1, 2, 3, 4, 5, 6, 7. So this point here will be moved to this point, and this point here will be moved to this point. So just like 5. To back. When we multiply x by 2, the PDF just expands for 2 times. And then we add a constant number, it just moves from this point plus to the, and plus the constant number to that place. This is an example when a is a positive value. So when a is a negative value, for example, y is equal to -2 plus 5. So when we want to find out the PDF of -2x, we just first flip this px, and then we expand it by 2 times. So this the PDF of -2x is actually equal to the PDF of 2x. So this can also represent the PDF of -2x. And then when we plus a constant number like +5, it's similarly moving from here to here. So this one can also represent -2x plus 5. So let's write it as the expression. For y equal to 2x plus 5, we can see that fy, the PDF of y is equal to f of x, replacing x by y minus 5 over 2. So we have a 1 over 2 in the front because we can see that this is 1 over 2, but this is 1. And we want to ensure that this area has the same area as this one. Y equal to -2x plus 5. This is 1 over 2 in front, and then this is -2 here. So notice that the factor in the front is always a positive number because the PDF cannot be negative. And inside we just replace x by y. This one. So from this result, we can conclude that fy is equal to 1 over the absolute value of a multiplies the PDF of x we always need to remember that this factor here is positive. And then give a simple example. All random variable. Fs is equal to 1 over X, and this is the variance of X. So f is a normal random variable with this PDF. And when y is equal to ax plus b, and a is not equal to 0, so that we can use this formula here. A. So that we just plug in this term into here. Okay. Simplifying this term, we obtain the following. We can see that this PDF looks very similar to this one. And actually this term this variance and this mean here. So we can say that y is also a Gaussian random variable with mean a mu plus b and variance a square sigma square. This example tells us that when we do a linear transform of a Gaussian random variable, we still obtain a Gaussian random variable. This formula is just like a shortcut of calculating the PDF of y when y is a linear function of x. So when we encounter this kind of example, we can just use this formula to obtain the PDF of y. Okay. That's all for today. So this is for the first part of the section 4.1. So in the next course, we are going to continue to complete the section 4.1. Okay, thank you.